Clicking through cloud consoles by hand works for a single server. It completely breaks down when you need to deploy thousands of servers across multiple regions before lunch. That scale requires infrastructure as code. Instead of relying on a human to manually click buttons in a web interface, engineers write out their exact infrastructure requirements in plain text files. Those files go into version control, meaning your entire cloud environment can be tracked, peer-reviewed, and rolled back exactly like software. AWS CloudFormation and Azure Resource Manager are the default starting points for this approach. They are cloud-native solutions built directly by the cloud providers for their specific platforms. Because AWS builds CloudFormation, it integrates with AWS identity systems and handles state management automatically behind the scenes. When Amazon releases a new feature, CloudFormation typically supports it on day one. But that tight integration creates a hard boundary. A CloudFormation template cannot speak to Google Cloud or Azure. Your infrastructure code becomes permanently tied to a single vendor's ecosystem. You get a frictionless, managed experience right out of the box, but you pay for it by giving up the ability to easily migrate your workloads anywhere else later on. To break out of that single vendor boundary, HashiCorp created Terraform. It operates like a universal remote control for the entire cloud computing ecosystem. With Terraform, an engineer can spin up an AWS database, configure a Kubernetes cluster, and set up Datadog monitoring alerts, all executed from the exact same workflow. To use that universal remote, you have to write your instructions in HCL, HashiCorp configuration language. It is a strictly declarative format where you describe exactly what resources should exist, without having to script out the steps to build them. HCL is highly readable, but it is proprietary. A team of Python or TypeScript developers has to pause and learn a completely new domain-specific language just to deploy their applications. Terraform breaks you out of vendor lock-in and gives you access to thousands of third-party providers. The entry fee is forcing your team to master a highly specific syntax that only works inside the HashiCorp ecosystem. Good infrastructure code is idempotent. If you run the same deployment script 5 times, the cloud environment should look exactly the same on the 5th run as it did on the 1st. To guarantee that consistency, Terraform relies on an external ledger called a state file. Every deployment, Terraform checks your code against the state file, applying only exact changes to make the live cloud match. But that file is sensitive. If it gets corrupted or falls out of sync, Terraform loses its reality map. It often contains unencrypted passwords and API keys. Operations teams explicitly design systems to protect it. That means configuring remote backends, like AWS S3 combined with DynamoDB, just to lock the file during concurrent updates and encrypt the sensitive data inside. Terraform delivers highly predictable, safe deployments at scale, but requires your engineering team to take on the permanent operational weight of managing and securing state. For teams that find declarative languages and state management overhead frustrating, Pulumi offers a different model. Pulumi abandons proprietary syntax. It allows developers to define cloud infrastructure using the exact same general-purpose languages they use for applications, like Python, TypeScript, and Go. By using these languages, teams can apply standard programmatic logic. A developer can use native for loops to generate multiple environments, or apply if-then conditions based on API responses, all while validating their infrastructure with standard testing frameworks like Jest or PyTest. Generating dynamic infrastructure in Terraform requires learning specific workaround functions and meta-arguments. In Pulumi, you just write standard software functions to build out your architecture. However, Pulumi's provider ecosystem is smaller than Terraform's, and giving developers the full power of a programming language means they can write overly clever, tangled infrastructure code that becomes nearly impossible for an operations team to debug later. Pulumi removes the barrier between application code and infrastructure code. It empowers developers to move fast, provided they enforce rigorous software engineering discipline to keep their environments readable. Whether you choose Terraform or Pulumi, defining infrastructure as text is what makes it possible to shift left, the practice of moving security testing to the very beginning of the development cycle. Instead of waiting until a database is running in production to discover it is publicly accessible, teams can scan the raw code for vulnerabilities before a single resource is ever spun up. This diagram illustrates exactly how that works. Code is pulled at checkout. passing through security tools like Trivy and SonarCloud. If they detect an exposed secret, they act as hard gates. The pipeline fails automatically, blocking the apply stage from ever executing. Building these policy as code guardrails takes significant engineering time up front, and the rules require constant updating to prevent false positives from slowing developers down. You invest heavy hours configuring the pipeline early on, but that investment ensures catastrophic misconfigurations are caught in a text file rather than in a live production environment. There is no objectively perfect IaC tool. The right choice depends entirely on your people and how they prefer to work. To decide, weigh language preferences, state management tolerance, and multi-cloud ambitions. For ops engineers wanting standardization across any cloud, choose Terraform. For developers building dynamic microservices, Pulumi uses logic they already know. And for single provider setups, CloudFormation eliminates state management entirely. Technical debt rarely comes from picking an inferior tool. It comes from forcing an engineering culture to adopt a workflow that fights against their existing instincts and skills. To see which approach resonates with your team, you need to look at the code yourself. Go to the Terraform registry, search for the AWS provider, and pull up S3 documentation. Read the HCL syntax and ask yourself if your team would find it readable or restrictive. In our next episode of the DevSecOps series, we will break down exactly how Terraform's architecture operates under the hood, separating the core engine from the provider plugins. Because at its core, automating your cloud infrastructure is the absolute baseline requirement for any reliable DevSecOps strategy.